So this will be the solution to question 10 on the 116 first exam in winter 21. And this question was looking at section 15.3 of the textbook. So looking at the mathematical description of sinusoidal waves, looking at essentially the wave equation given here. So trying to determine, in this expression allows us to determine the vertical displacement of a wave at some horizontal location x at some particular instant at some time t. That is a function of the amplitude of the wave, the wavelength, and the period. So that's basically what this question was pertaining to. So the question itself, so the context here is, so while sitting at the dock of a lake, a Physics 116 student notices the vertical oscillation of a duck in the water. And the student takes a photo of the duck when it's at the top of the crest of a wave, so sort of indicating here that we're looking at a cosine wave, and that we have a positive displacement at x equals 0, and then later creates the image below. Okay, and then we're told that the student also determines that the wave moves in the positive x direction with a velocity of 1.4 meters per second. Assuming that the duck remains in the same horizontal positions, assuming that they remain at x equals 0, what would be the vertical position of the duck if the student had taken the photo 3 seconds later? Okay, so with this question, as I mentioned, it's getting at the wave equation. So we're looking at yx of t as a function of x and t is given as a cosine 2 pi over lambda times x plus or minus 2 pi over t times small t. Now in this particular question, we know that the duck's position is x equals 0, so x equals 0, so we can simplify. We can just remove that entire term in the parentheses, 2 pi over lambda times x. And we know that the wave is moving to the right, so technically we have a negative sign in the expression, but for this particular context it wouldn't have mattered. So yeah, so we're looking at basically what is the value of y at a position of 0 at time 3 seconds. So what we can go ahead and do here, change this. I'm going to write this sort of more generally, because there was two versions. So we can do a cosine negative 2 pi. Now we're not given the period, and we're only given the velocity and so basically we have the velocity and we also have the wavelength. So maybe as a separate note here, the velocity of a wave is given as how far it travels in one period. So we travel the wavelength in 1 full period t. So t itself would be then equal to lambda divided by v wave. So if in a sense, I'm going to replace this t, in the uppercase t, the period, with lambda divided by v wave, so the v wave comes to the top, so I'm left with lambda times v wave times t. The negative sign there in front is already including, taking into account that the wave is moving to the right. So no matter what version you have, this expression will give you the correct answer, where the amplitude is, of course, in this example, 0.4 meters. I think that was true for both cases. I think the only thing that was different, I think, was the speed. I think one case was 1.4, the other case I think was 1.2. So that's the amplitude can be read from the graph, and the wavelength, of course, can also be read from the graph. This is lambda. So again, if you look at your graph, so in this example, the wavelength is 6 meters, the amplitude is 0.4 meters. And I might have gone too far actually with the arrow there for the amplitude. Yes, the 0 line here. So it's oscillating between 0 and plus 0.4 and negative 0.4, so that's 0.4 would be the amplitude in this example. And the wavelength is 6 meters. We're given the v of the wave in the question. The time is given as 3 seconds later. That's our time indication, and we have basically at that point we have all the terms. At that point we just plug it into the equation. So for this particular example, the y at 0 meters at 3 seconds later works out to be negative 0.12 meters, and for version B, the y is equal to negative 0.32. And that's the case where the velocity, I think, was 1.2 meters per second. Okay, so yeah, the question 10, definitely on the wave equation, but sort of placing the duck and not having the duck move relative to the water allowed us to cancel out that first term and just focusing on the second term, but also there's a little bit of work in determining the speed of the wave in terms of the period, or the period in terms of the wave speed, in order for us to be able to determine all values. Yeah, okay, so I'll wrap that question up there and follow up with question 11.